now please, let's give a round of applause to King of Plumbers from Polymer Labs, Bo Du.
Hey everyone. It's a big stage. It's very wide. Hey, my name is Bo. I'm here to talk today about building the future of IBC. But first, I wanted to say a few words about Polymer Labs. We're an organization with a singular focus on bringing IBC to all chains and making IBC faster to integrate and accelerate IBC adoption. A little about myself. My background is in distributed systems and database systems. I previously worked at a number of startups. I worked on an open source time series database. I see blockchains as just another database. So to frame the conversation today, I want to talk about a few of the challenges that are limiting IBC adoption. There's the scalability of the IBC network topology, a slow pace of integrations, poor developer user experience, lack of framework integrations, and insufficient coordination. We're going to dive into how we're going to address each of these challenges, and I also have two major announcements incoming in this talk. To start, I would like to talk a little bit about how to scale IBC network topology with multi-hop IBC. Currently, in the IBC network, chains have to directly connect with one another or establish IBC connections directly for applications on those chains to communicate with one another. With this topology, we get O of n squared scaling with the number of connections. With multi-hop IBC, we can scale the network topology with O of n connections. Chains are no longer required to establish direct connections for applications on them to talk to each other. We can see in the diagram that with multi-hop IBC, applications can establish an IBC channel across a number of pre-existing connections. So the prior thinking around multi-hop was around how do we send packets over multiple channels and connections. As we can see in the top diagram, we have a packet that starts at one path end, and we write that packet to each and every intermediate hop before arriving at its final destination. This complicates a number of things, including application protocols like relay incentivization. With multi-hop IBC, we can the packet will start its journey on one path end and immediately arrive at the other path end, allowing for direct communication over a number of hops without requiring writes to these intermediate hops. This enables a multi-hub model and a multi-hub and spoke model that improves the efficiency of the network. It also allows for heterogeneous network topologies. Chain diversity means client diversity. As the IBC network expands, we're going to see a growing number of different consensus algorithms in the chains, different state commitment data structures. If every chain has to connect directly with every other chain, this means exposing these internal implementation details to the entire network. With the multi-hub model, any middle hop can be a hub for any subset of the network. Multi-hop IBC means that the spokes of each of these hubs can communicate with one another without being aware of all the implementation details of the rest of the network. One of the most limiting factors for IBC is that we are not able to integrate IBC fast enough into new chains, new frameworks, and so on. So I want to talk a little bit about how Polymer can enable fast IBC integrations. But first, I want to review the interoperability model. On the left-hand side, we have the OSI model, as many of you are familiar with. And on the right-hand side, we have the Web3 interoperability model. At the application layer, we have HTTP and gRPC, which is analogous to various IBC application standards like interchain accounts, token transfer, and so on. At the transport layer, we have TCP and UDP, which is analogous to IBC's channels. And at the state layer, we have physical network links, which is analogous to IBC connections and clients. So in the context of IBC for Cosmos chains, we have these same three layers. We have app, transport, and state. The application layer is in the form of various IBC application standards. The transport layer is in the form of an IBC Go implementation or the IBC core implementation. And the state layer is implemented as various light clients. IBC, as you know and love it, looks like this. We have app, transport, state. An application is able to establish a channel from one chain to the next over a connection established at the state layer. And it can send packets over this channel. But what if I want to enable IBC quickly on a new chain? We can see in this diagram here that on the non-IBC chain side, we have a number of missing boxes. Now, what are these boxes? We have a missing transport layer implementation. We don't have IBC natively implemented on this chain. We can't commit to the IBC data in a way that the rest of the network understands. At the state layer, we also have a client problem. We need to be able to verify the state that's being transmitted from the IBC chain. Normally, this is in the form of a light client. In the current IBC network, that would be a Tendermint light client. The challenge is with doing this natively. So if you want to integrate IBC natively into the chain, the IBC transport implementation natively into the chain, it's time and resource consuming. There's a number of teams that have tackled this. It's taken them a lot of time to introduce them to just singular networks. At the state layer, we have a problem with verifying the consensus of the IBC chain. Naive verification of Tendermint consensus on a chain like Ethereum is cost prohibitive. So how do we solve this problem? The first step is we can introduce Polymer as a middle hop. Generically speaking, when we introduce Polymer as a middle hop, we get this setup here. So we're able to establish a multi-hop channel over Polymer as a middle hop, and chains and applications on chain A can communicate with an application on chain B over two connections established between chain A and Polymer, and between Polymer and chain B. However, in the case that chain A is not a native IBC chain, we have missing boxes here. So IBC transport does not exist on chain A, and an efficient Polymer light client does not exist on chain A as well. So how do we solve this? The second step, we're going to outsource the transport layer to Polymer. Polymer's core idea is that we want to decouple the IBC application and transport layers. In doing so, we make the boundary between the application layer and the transport layer asynchronous. We call this protocol virtual IBC. This means that on chain A, we have a binding between the application layer, an asynchronous binding between the application layer and the transport layer on Polymer, which we call virtual IBC, and a connection between the two, which we call a virtual connection. And chain A now becomes a virtual chain. And in doing so, Polymer redefines IBC extensibility. We're able to establish a channel over Polymer efficiently to allow applications to communicate and add IBC transport to this new chain. We no longer have a native IBC transport implementation on chain A. Now we have a virtual transport implementation. This virtual transport implementation is bound to the IBC transport implementation on Polymer through virtual IBC. To solve the problem of the state layer, we built ZK Mint, which allows us to efficiently generate ZK consensus proofs for Tendermint consensus on the order of seconds. We're also able to verify these proofs efficiently on the virtual chain. A non-obvious design goal of ours was that we wanted to make a real drop-in replacement for native IBC. We wanted to make it so that a multi-hop channel can switch between virtual connections and native IBC connections transparently. In doing so, virtual IBC becomes interchangeable with native IBC. Another huge problem with IBC is the issue with developer user experience. The developer user experience of building app chains is already pretty good. We have Cosmos SDK. The framework and the tool chain around Cosmos SDK is already becoming quite mature. However, building a decentralized application across multiple chains in the IBC network is quite challenging and difficult. There are a number of competing protocols working and focusing on this developer user experience, building tooling for their protocols. So to compete with them and to make IBC stay competitive, we're introducing my first major announcement of this talk, which is IBC SDK. Now, what does IBC SDK do? We abstract away all of the complexity of IBC infrastructure away from the application developer. Everything beneath the application layer across the IBC network is now replaced with IBC SDK magic. Now, what is it actually doing? It simplifies developer user experience by bringing up chains and hubs, configuring paths on relayers, bringing up relayers, managing deployment of smart contracts, creating clients, connections, channels, orchestrating containers, and more. So a personal story of mine, I spent some time working on building cross-chain applications in early 2021. This is very, very early on the interop side. Applications were just starting to expand beyond Ethereum onto other chains. And the developer experience was quite poor. The framework that I was using and building upon meant that I had to wait a long cycle between each iteration of making a change and seeing the effects of those changes. This slowed down development and made development quite painful. In fact, I tried to convince one of my friends to work with me in Web3. He went through this process, he hated it, and he now has his own database company. So unfortunately, we couldn't keep him in the ecosystem. But with IBC SDK, we can take snapshots of chains, of production state of chains, spin up a network that mimics the real production state of all of these networks, and configure these chains to have very low block times, and enable developers to have a very fast iteration cycle over their build process, to enable a very nice developer user experience for developers. Another problem is the issue with the lack of framework integrations. And what I mean by this is, recently we've seen a lot of various frameworks come up to build rollups, roll apps, sovereign or otherwise. In the future, a lot of activity from various L1s will likely shift to the various L2s. For example, on Ethereum, a lot of Ethereum activity will likely shift to Ethereum L2 activity. Unfortunately, we missed the boat with a number of these L1s on getting native IBC integrations into them. So it's much more important that we get a native IBC integration into these various frameworks. A native IBC integration into these various rollup frameworks will mean that rollups on Ethereum will be interoperable with one another in a standard way that also makes them interoperable with app chains and app rollups and rollups on Celestia and other ecosystems. Standardizing around IBC transport is incredibly important. Other work that we have is work to make relayers dynamic and fee aware. So currently, relayers are not aware of fees. Relayer incentivization and fee incentivization has yet to come live. But when it does, we want to allow infrastructure providers to be able to run these relayers at profit. And they can only do so if the relayers are fee aware and can dynamically adjust to market conditions. Another main issue is that we needed more SDK agnostic IBC implementations. For example, IBC Go has a lot of Cosmos SDK-isms in it. So when I chatted with multiple teams that are trying to integrate IBC into their chain, even if they're using Go, they're having to fork IBC Go. They're having to take code out of it. They're having to maintain their own fork, which is not great because with the pace of IBC development as it is, they're going to fall behind, and it's going to make integrating IBC less and less ideal if they have to maintain a full fork of IBC with the small team or resources that they have. There's also other open research work to implement fraud-provable IBC. I can imagine a world where we can generate fraud proofs for IBC, the execution of IBC transport logic, by compiling IBC Go to MIPS, the MIPS instruction set, and pairing it with a fraud proving system such as Canon by Optimism, which supports MIPS. So how do we take ownership of IBC expansion? We currently have a lack of coordination and focus, which is limiting IBC expansion. It's difficult for new contributors to determine what to work on, gain sufficient context to execute, and get the funding and support that they need for their efforts. There's also a lack of ownership over important initiatives, a flourishing ecosystem of open source projects, insufficient coordination across the community and across teams, and it's unclear how to financially support both general open source development and also specific initiatives. So how do we solve the coordination problem in order to expand IBC? This brings me to my final announcement of today. We're excited to announce Open IBC as the solution. It's an organization with a mandate to expand IBC across all networks. It values an independent action and loose consensus. It prioritizes the highest impact problems limiting IBC adoption. It also organizes events and rallies communities around the world towards a common goal of establishing IBC as a universal interoperability standard. It also supports and maintains official open source projects in the IBC ecosystem. So I'm calling on you in the audience and future viewers of this presentation to join us in building the future of IBC. Thank you. After the talk, oh, sorry. After the talk, we have a demo coming up in the workshop room by our DevRel, Thomas, of our protocol in action, of IBC SDK in action, and an IBC packet going from a Cosmos chain to Ethereum. Thank you.
Thank you, but we actually have one question for you. So
Okay, yeah.
It just showed up here. If I'm going to read something wrong, I'm sorry.
Okay.
But there's a question from Anonymous, and they're asking, reliers are an integral part of the usage of IBC across chains. However, currently there are no initiatives for running a relier. How can we insensitivize them?
Yes, so relayer incentivization is a big problem. There's a specification that's been finalized for incentivizing packets. So there's two jobs that a relayer needs to do. One is relaying packets from chain to chain. And the second thing that a relayer needs to do is also submit client updates. It needs to make the chains, or the counterparty chains in an IBC connection, aware of each other's state. Those client updates are very cheap within the Cosmos. So my understanding is a lot of relayers will get funding or some sort of grant. Sometimes they run at cost. When you want to connect to a chain like Ethereum, that connection becomes much more expensive to maintain. So we need to encode proper relay incentives for not just packets, but also client incentives as well. I have a spec proposal in the ICS repo for introducing client update incentivization to the existing relayer fee incentivization for packets. So with client update incentivization and packet incentivization and dynamic relayers, we'll have a flourishing ecosystem, or a dynamic ecosystem, a dynamic marketplace for relayer fees, and relayers, validators, and infrastructure operators will finally be able to run this infrastructure at profit.
All right. Well, thank you. Thank you very much.
Okay.
Thank you.
Okay. Thank you.
Yes. Thanks.